permutations and how to generate permutations and how to use this in various kinds of exhaustive search, right? So I like to start with this. I should put this on. Where's my mouse? Oh. Okay. So I like to start with this because often people don't understand what exponential time means. And so I have this little table. Let's say that I have three different algorithms, and for a given input size, let's say that the linear time algorithm runs in 10 seconds, and so does the n-squared algorithm, and so does the exponential time algorithm. So then you're going to say, what's the difference? All these are good, right? But you have to see how this time grows as n grows, and that's where the difference really shows up very, very clearly. So you can look at how things change when you go from 100 to 101 to 102. In the linear time, it's going to grow linearly, of course. So that goes 10 to 10.1 to 10.2. With the n-squared algorithm, it's a little more complicated, but you can kind of figure this out. So instead of 10 seconds, you're going to get 10.2 seconds, then 10.4 seconds, and so on. There's a little calculation that you have to do, but I'm sure you can figure that out. The tricky part is in the exponential one, where each increased value of each unit increase in n will essentially double the time. And that's because n is in the exponent, right? And the base is 2, so therefore it'll double. If it's 3 to the power n, it'll triple for every increase in n. And so 10, 20, 40, and you can see the difference. It's just shocking. So even though you might get fooled into thinking that for n equals 100, they're the same time, it's really the big problem is in how it increases. It becomes even stark when you try doubling the value of n. And there you see the changes. Linear, of course, will double each time. And n-squared will go 4 times each time. And this guy will just go, it'll square each time, essentially. Right? Because 2 to the 2n is 2 to the n times 2 to the n. So essentially, it'll get squared. So 10 will become 100, 100 will become 10,000, and so on and so forth. So this is where the issue is with exponential time. So in general, that's why we avoid trying to write brute force exponential time algorithm, even though they might look simple and might actually work fast in simple cases. They don't scale very well. That's the problem. So that brings us to permutation generation. Here's a list of all permutations of length 3. Hey, hi. Hi. Hello. Hey, David. Long time no see.
I know. You remember me?
Yeah.
I'm here today. Make up for
yeah.
all those other days.
Yeah, semester did get crazy for a bit, right?
Yeah, it did.
Yeah. Yeah, I'm hoping it'll get better. So this is just a simple example of all permutations of the first 3 numbers, 1, 2, 3. And you probably remember from your discrete math days that there are n factorial different permutations. So if there are 3 numbers, then 3 factorial is 3 times 2 times 1, which is 6. And that's what you see. You see 6 different permutations. So for n equals 4, you should see how many?
24.
24, right? So here are the 24. And what you see is that essentially there are 6 of these starting with 1, 6 of these starting with 2, 6 of these starting with 3, and then 6 of these starting with 4. The other 3 values are simply permutations of the remaining numbers, which will follow what you had before. Right? So that's one way to write this down if you were to do this manually. There's some method to this madness. It's possible to write this down, but when n starts to get larger, it's a little too crazy, so you want to write a program to do this. So that's what we're going to look at. We're going to see how to write a program to generate these permutations. And the annoying thing is that it looks simple, it looks deceptively simple, but it's not that trivial. If you've done it before, then it's very simple. If you've never done this before, or if you've never thought about it, then it becomes quite tricky. How many of you have written a program for permutations? Yeah? Okay. All right. So for those of you who haven't, it requires quite a bit of thought. I'm not sure I could write this very quickly if I'm asked to write this code. So it's a good idea to know this, and if you ever compete, this is something that you want to keep with you, because it's simple, short, but it's not something you want to try and figure out in a competition. So here's the pseudo code for permutation generation. It's, as you can see, the function is called visit, although I could have called it anything I want. And you can see that it's a recursive function. Now, what exactly is happening here? Well, you're assuming that there's a main program somewhere from which this is called. And you will call this with u equals 1. And what it'll do is it'll do what we saw on the previous slide, namely it'll generate all possible permutations. So we're going to try and go through this code and make sure that we understand this. So here it assumes that it has generated some permutations, and well, it'll become clear as I work through some of this pseudocode here. It's kind of hard to explain what this function does. It's probably useful to start with an empty array. So it assumes that there's an array, and the array is called val, or values. So here's my val array. And let's go with n equals 4, something simple and small. And we're going to have a variable called count. And we're going to have a variable for, that's it. Those, well, you need u and v. These are your variables. Now, to start with, we're going to assume that everything is in this array is a 0. And we're going to assume that count also is initialized to 0, and that the first time you call this function, you're going to call it with u equals 1. Okay? So you get into this function, and the first thing it does is it puts in location u, it puts the current value of count incremented by 1. So count gets incremented by 1 first, and then that goes over here. Okay? And it checks whether count is n. When count is n, we assume that the array has been filled. If the array has been filled, you have a permutation. You just print it out. So that's what the next statement is. If count is equal to n, then just print the permutation. So whatever is the current content of this val array, that's the permutation, and you print it out. But that's only one permutation. And then it's going to keep going. Now, how does it keep going? Well, if count is already n, then of course there's nothing to do here. And it will decrement count. It will zero out some values, and then backtrack and continue to the next permutation. Okay, that's the general plan. So plan is print out a permutation, backtrack, change some values, and go and print the next. Okay? Now, so let's look at what happens in this main for loop, because that's where the heart of the code is. At any given time, things are going to look like this. Part of the array is filled up, and part of it is all zeros. And this count keeps track of how many of these values are not zero, right? And the moment this becomes n, you've got one permutation and you spit it out. Okay, so if count is not equal to n, well, by the way, I could have made this an else part, but I probably should have. It'll make it for more efficient code. So I think you should make this else and then push the for loop out a little bit. Yeah. Then it uses a new variable called v, goes through all the possible values, and checks for the first 0 item. The first 0 item is the one that it will focus on, and it'll make a recursive call for that value. So over here, the first 0 value is in position 2. And so therefore, it's going to call visit of 2. OK? Are you with me so far? So when it restarts, u is now 2. Count is 1. And u has become 2. So instead of changing this, what I'm going to do is to draw the recursive stack, because this is recursion. If you don't do this carefully, we'll get completely confused, because some of these are local variables and some are global variables. Now, which ones are local and which ones are global here? So value and count are global variables. This and this are global variables. U and V are local. Okay. So these are the local ones. So what I'm going to do is to draw a recursive stack where I will only keep track of the local variables, because the global variables are fixed. And I am going to so I'll just have u and v here. So the first time around, when I called it, I had u equals 1. And then I found v to be equal to 2, and I made a recursive call with that value. So the next recursive call sits on top of this. This time u equals 2 because you called it with v, right? So now we're going to restart the whole procedure, whole function, but u is now going to be equal to 2. Are you all clear with this? Great. So when u equals 2, it's going to put the next value of count in position 2. So over here, this gets 2, but before that, it has incremented this to 2. And now, again, count is not n. So it's going to go down here, going to find the first 0 value, which is going to be 3. And so I'm going to then get v equals 3. And I'm going to make a recursive call, u equals 3. And I'm going to restart the whole thing. This time, count becomes 3. And this becomes 3. And it will restart the process, right? So count is still not n. So it's going to find the first 0 value, which is 4. And so v will be equal to 4. And it'll make the recursive call. So this time, u is equal to 4. And it starts at the top. It puts in the value 4 here, right? And then this time, count is 4. Oh, I forgot to update this to 4. This time, count is 4. And so it's now ready to print out a permutation, which is basically the contents of this array. And so you print out 1, 2, 3, 4. All right, now comes the tricky part. Let's see how it backtracks and figures out what to do next. So what it does is it continues here. when u equals 4, it's going to go through this whole for loop and not find a 0 entry. And so it'll come down here for the backtrack part. And the backtrack part says decrement count. Yeah. Make this a 0. Right? Yeah, okay. And finish the recursive call. So this guy goes away. And you're back here. Here v was already 4. So this for loop, we were in the midst of this for loop, and the value of v was already 4. So that means it's going to finish up and go over here. Is that clear? So therefore, count is again going to be decremented, and it'll become 2, and it'll turn this into a 0. And this recursive call finishes up. It's going to go over here. This time, it's finished with v equals 3. And so this time v is going to be equal to 4, and it's going to make a recursive call, but with u equals 4. So let me continue the stack over here. And we have u equals 4. Fine? So when u is equal to 4, we're right there. Count is now 2. So it's going to increment count to 3 and put it in position 4. Okay. And then it's going to go look for the next first 0 entry, which would be here. And it would go and make a recursive call with u equals 3. And I won't draw all that stuff, but what you should expect is that this will become 4. And at that point, count will become 4, and you'll print out the next permutation, which would be 1, 2, 4, 3. Yes, David?
Are we building a string?
We're not building a string. It's really an array. You can do what you want with it.
Okay.
If you want to build a string, you could. Yeah.
There's a way to traverse it. The permutation would be printing a string
So,
to build.
right. So think of this as a permutation of the numbers 1 through n. You can modify it for strings. You can modify it for anything else you want, and we'll talk about that once we understand this completely. For now, it's just a plain permutation on n integers, the first n integers. So this is sort of the most basic form of permutations. Yeah?
In the main function,
Yeah.
we have to
call with this with u equals 1. Yeah.
Wait, equal to 1, or do you have to do 1 to n?
You'll call it with, oh, you're right. So we'd have to call it with 1 to n. You're right. It'll need a simple for loop. That's absolutely right. Okay, so let's try and figure out how it handles the next step. Once we understand that, it'll become a little more clear. So we did u equals 4, and at that time it called v equals 3, right? Then it went u equals 3, and at that time it finished up, and we're going to return from here, and we're going to return from here, go back there. This is 4, so there's nothing more to do, so therefore this one will also be done. It'll go down here, right? And at this point, it's going to try out v equals 3. So you have u equals 1. So let's look at the content of the array, because it would have blanked out some things. This should have become 0. This should have become 0, because it backed up from there and did this. And this also is now 0. Count should be 1. Went through several backups, right? So we have only a 1, and then we have all zeros. Okay, good. So now we look at what's happening here. We finished with v equals 2, so we're going to try v equals 3. We check that, well, 3 is the first, 3 is the 0. And so therefore, it's going to call visit with 3. So what we have is u equals 3, and it's going to go and find the first 0 item, which would be in position 2. Is that clear? But before that, it's going to make this guy as 2. Right? Because count is at 1, count will be made 2, and 2 will be put in position 3 at position u. So you get a 2 here, and then the next time it'll go find it, and you'll put a 3 here and a 4 here. That's what will happen, right? So I'm skipping some steps here, but you'll see that it will print out 1, 3, 2, 4. And then what would be the next one if it goes through the process? 1, 4, 2, 3. 1, 4, 2, 3. So 1 and 2 would be fixed. The other 2 would finish up. Then what would be the next one?
Wouldn't it be 1, 3, 4, 2?
Huh.
After that one.
Well, so that's what you have to you have to look at what happens. 2 is it has put 2 in position 3. Yeah. That's fixed. Then it goes through 2 recursive calls where it'll find the first 0 item, and that's where the 3 will come, and that's where the 4 will come. This will get, and then when it backs up, this will become a 0, this will become a 0, not this. Because that's what's on the stack.
Okay.
Right? Because it's just following the stack. And on the stack, you also know what counter you have for the V. And the counter for V says that V was 2, not 3. All right? So it'll go and check 3, but 3 is not a 0, and so it's not going to touch it. Okay, so this is actually correct. So if you understand this, what would be the next one?
1, 2, 3, 4.
1,
2, 3, 4.
that's already done. That would be a mistake if it did that. Where would it put the 2? That's the question. Yeah? Because think about what's happening. You're going to backtrack until count becomes 1, right? So only thing that's fixed is this. Everything else should be a 0.
Yeah. Oh, now the 2 is 3 at the end.
But what you'll see here is that V equals 3 is finished.
Yeah.
So it's going to go to V equals 4. That's where it's going to put the 2. Okay? So 2 goes here, and then the other 2 need to be filled up. So when it finishes, it's going to have 2 here. Then it's going to go look for the first 0 position, which would be here. That's where the 3 goes. And then this is where the 4 goes. And it's going to spit it out, correct? And then when it backs up, it'll back up these 2 guys, turn them to 0, and then it'll flip them. Because 3 will get put over here first, then the 4 here. So you'll get 1, 4, 3, 2. Are we clear about this? You want me to go over this more slowly? Because the recursion is tricky. Are you okay with this? Okay. What would be the next one?
All the ones.
Where would it start?
The first one, we called it on 1. Yeah, now we
Yes.
call it on 2.
Yes. So what's the first non-zero item that's going to be put into the array?
2? No? Is that what?
It always puts count.
Oh.
Right?
Yeah.
Because that's the value that gets put in the array. So it always goes back. Remember, now it's going to back up all the way to a completely blank array. But count is going to be blanked off to 0. because it keeps decrementing it. And so 1 is the value that's going to be put wherever.
At position 2.
It's going to be put at position 2. That's it. Yeah, is that clear?
Yeah.
So whatever comes out will have 1 in the second position, and you'll have that. And then it'll go through the motions. It'll put 2 here, 3 here, 4 here. The 1 will stay there, and it will back up the 3 and 4, and those will become 4 and 3. Then it'll back up, and it'll blank this out and put the 2 over here, right? And the 3 and 4 will go here, and then 1, 2 will stay there, 4 and 3, and so on. Does that make sense? Yeah? So you can now figure out the rest of the order. So it's not the same order that we wrote down on the previous slide. It's a slightly different order. What it does is it fixes the position of 1, then it fixes the position of 2, then it fixes the position of 3, and so on. Right?
It's on indexing on the.
It's on the index, that's right. Yeah, absolutely right. Yeah, yeah. So it's a little confusing, that's why I wanted to go through this code. Yeah? But it's useful because you can use this as a template for so many different problems. Right? And I definitely recommend that you guys write up this small code and play with it. Understand, make sure that I was right. Whatever I claimed here, that it's true. Yeah?
Well, yeah, because at the end you would just print out the value
Correct.
on that table.
Yeah. So there's a lot of stuff that goes on in the background, but in the end, that's the output you get. Okay. Any questions about this? Now, just quickly, how do I prove this is correct? I mean, we wrote up something. Why would you expect this to be correct? Do you? I just want to talk about program correctness or algorithm correctness. How would you prove that this is correct? Any thoughts on that? It might help you to think about other problems as well, so I thought I'd go through this exercise.
So we know count is never going to be the same for during 2 recursive stacks.
Okay.
Calls.
So that means you'll always get a permutation.
A permutation. And then we know that.
No, hold on a second. So you get a permutation if no number gets repeated, and you're saying count is always incremented, and so that's not going to happen. But how do you know it doesn't go and find the same index? You also have to make sure that the index is clean, but because it always finds a 0 entry, that problem won't occur. So therefore, you're always going to get a permutation. So the first thing you proved was that when it prints out, it always prints out a permutation. That's the first thing we figured out, right? Let me write here. So whatever that statement is, if count equals n, it always prints a permutation. That's what you just showed me, right? What else? Is that enough? Clearly not, right? What else do I have to show in order to prove that this is correct? Yes, sir?
That every output is different from the rest? Like
that you get that no permutation is repeated. That's what you're saying. Okay? How do you prove that? That looks crazy. That looks difficult.
Well, there's also that, and that the amount of things that you print out is n factorial.
That's right. So the last thing is, so first of all, you want to prove that every permutation it prints is unique. And secondly, it doesn't miss any, which is the same as saying it's n factorial. So how do I prove that no permutation gets printed twice? Not so easy, right? Yeah, go ahead.
You can put it into a hash map, I guess, and then see
Well, but that's verifying. I want to be, I've written this code. How do you convince me, how do you convince yourself this will never repeat a permutation?
So it first at the beginning of the stack, right? You're always changing where the 1 is. So therefore, every subsequent recursive call will have the same, 1 in the same position.
Yeah.
And then
So the trick sort of is in this for loop, right? Because when it backtracks, it increments the value of v. And so therefore, that same value is going to go into a different location, and therefore the permutation has changed. And what's also true is that the next value always goes further out, right? And so therefore, it cannot go and print a previous permutation, right? So in the ith iteration, so to speak, it's not really an iteration. When count is equal to I, it's going to try and put I in some location, and it finds a different location every time, and it goes out all the time, right? So it's possible to prove that no permutation is printed more than once. So finally, it doesn't miss any permutations. How do I prove that? That looks even more crazy.
I guess here U can be placed in every index, and then
Yeah.
every other U's or every other numbers could be placed in the length of the array -1 and then -2, then multiplying those, that's how you get the factorial.
Yeah. Perhaps that's enough. I'm not 100% sure. Let's hear out. You did something?
Like we can see that the code doesn't just go through. It doesn't just check all permutations, but all possible strings you can get from 1 through n.
Yeah.
And then it only spits out a permutation.
And the for loop doesn't skip any values 1 to n.
But how do I know in the end I have n factorial? So
You multiply all the u's.
multiply all the u's.
That's n factorial.
Okay, yeah, so you guys all have the idea, but it might, the formal way I would do it is by using induction. So let's assume that this works perfectly well for a certain value of n, or let's say all the way up to n minus 1. Now I want to prove that it works correctly for n. Now, how do I do that? Well, what it does, we know, is that it first fixes the value of 1, or position of 1, and then all that it does is essentially permutations of the other numbers in the other locations.
Yeah, it does it n times.
Yeah, and it does that, and so you have to do this n times, so therefore the number of print permutations is going to be n factorial, and then all that would work out. That's one way to do it. There are other ways to do it, of course, but that's how I would approach it, by induction. So I just went through this because sometimes we write complicated algorithms and we have no idea whether it's right or not. It helps to structure your thinking so that you know you're on the right track. Okay? All right, so that's permutation generation. Let's try traveling salesperson problem. Let's say you've given a graph, and I ask you, can you print all possible traveling salesperson tours off this graph?
Could you define the traveling salesperson?
Sure. So traveling salesperson problem says you're given a graph. Every edge has a weight. Okay, this edge from F to E has a weight. I know you can't read the number, but it's some number. Okay. And your job, for now it's a simpler job. Your job is to list out all possible tours where going from one city to the next city is a valid edge. So you can't have F followed by L because there's no edge between them. But you can have F followed by E or D or A. Does that make sense? So your entire tour has to be correct. Also, in the end, you have to come back to the start point. That's the traveling salesperson tour problem. Now, the question is simple. Print out all possible tours and print out their lengths. Yeah.
So I guess I time back to the permutation. Because
Right.
the permutation
So it's basically a permutation problem.
But
It's clear, right?
We have to check if there's an edge between U and V.
Correct.
Okay.
So you go through the permutations. So yeah, one simple way is just do all the permutations on n numbers, on whatever n vertices, and then cross out all those that have successive items that are not connected by an edge, right? That's a simple way to do it.
It's like DFS on each and every node.
It's not DFS. DFS is going to die because DFS goes all the way. If it can't, it backs up and goes and switches direction. That's not what you want,
Okay.
because you want to be able to just do the tour, right?
Right.
And you're not allowed to visit any vertex twice.
Yeah.
So it's not a DFS. So DFS doesn't work. Okay.
What if it's like a table where you have to uncolor it, maybe, when you backtrack? Like how you
Well.
did it before?
So the first thing I want you to do is to understand that this is a permutation problem. That part is clear. We know how to cross out things that don't work, right? The second thing I want you to think about is we have this code for permutation generation. How do I fix this for TSP generation? Instead of trying to think about this from scratch, thinking about DFS or other things, think about how you're going to fix this instead, because that's an easier approach. Okay?
So where it says if value at v is equal to 0,
Yeah.
where we're checking if we're visited,
Yeah.
we also have another check where we check left and right. If there's an edge, then we can keep going. If not, just ignore this.
Right.
And then
So,
count at
so
n.
when it finds that first 0 location, that's the guy that's going to be next. So unless there's an edge, I don't make that the next 0. I don't make that the next one. That's all that I'm going to change. Is that clear? So that's a lot simpler approach than trying to think about this from scratch with DFS. Yeah.
But now we won't necessarily get n factorial, right?
Well, we won't get n factorial permutations. That's pretty clear.
Yeah, yeah.
But we are going to go through all the n factorial
yeah,
permutations, essentially,
Yeah, okay.
right? And so that's the good part. So here's the code, pretty much what Ricky said. Instead of if val equals 0, we're going to also check if that next guy is an edge. Yeah, I could have put that below this as well. This is perfectly fine, or you can put them both together. Up to you. So you want both these conditions to be true. You want u to v to be an edge. And you want the v to have been not visited. Right?
Before printing out the TSP tour, we'll have to add the first node that we saw.
Yeah. So again, in the main program, there is a for loop.
Okay. Yeah.
You will try different start points. Unfortunately, different start points don't necessarily give you unique tours, because it's a tour and it goes back to the start point. So there are going to be some repeats. If you don't want those repeats, then don't do the for loop in the main program. Take that out, have only one start point, one, and that's it. Anyway, you have to visit all of them.
Yeah.
Doesn't matter where you start. So you just call this once with u equals 1, and you're done. That way you'll be guaranteed that you will never, will you be guaranteed? Yeah, you'll be guaranteed that you will never print any tour again, let alone any permutation. Okay? So in fact, that's already an improvement over the n factorial. It's now n factorial divided by n, so it's only n minus 1 factorial. Now the question is, are you still going to do n minus 1 factorial? Is that what, can you improve on this? That's the next question that we're going to ask. So the TSP tour, this one, in the worst case is n minus 1 factorial. How can I improve this? That's the next thing we're going to be thinking about. Here is the picture of an exhaustive search. I know this picture is awful, but you can see roughly what's happening. I'm always going to start from A, which is the same as our vertex 1. A has only 3 neighbors in this picture, right? A has neighbors F, B, and G. So those are the only guys that can be number 2 position. And so your exhaustive search will try those 3 for position 2. And then you see how it progresses. And because we are ruling out things that are not connected by an edge for the next position, a lot of the tree has gone away. So this tree is not your n factorial size tree. It is a lot smaller. But how small it is depends on the actual graph. If your graph were a complete graph, then it could still be n factorial. N minus 1 factorial, right?
That's when every node is connected to every other.
Correct. So I still go back to the question, how do I improve this code? Any thoughts on this? So here's a clue. Let's say that I try A, B, C. Let's say my first 4 vertices are A, B, C, and E. Because I may be searching from A. Let's say I go to B. From B, I find a neighbor, that's C. From C, let's say I find a neighbor, and that's E. If I start off my path as A, B, C, E, do you think I could finish the tour? Do you think I'll finish a tour? No. Why?
We have to revisit E at some point.
Right. Well, why do we have to revisit E? Can you articulate that?
Oh, wait, does this depend on if the degree is odd or even? Is that what?
No,
Oh,
it's a little more than that, yeah.
Well, because, I mean, like, the idea is that it's a dead end, so we can cache the dead ends.
Well, E is not a dead end. He has neighbors, so what's the problem?
Well,
But you
it
can't
could be
go
that
from
you
C.
already explored those neighbors, right?
No, I mean, G, L, F. So I just came from C. I haven't explored F. I haven't explored G. I haven't explored L. So what's wrong?
When we go around, we're going to have to revisit E at some point. So
Why is that?
because if we like if we go down to L and G, then we can't go down to F.
If we remove the nodes A,
Yeah.
B, C, and E, then we have 2 components.
Very good. So that's the right answer. You have something called a separator. Your A, B, C, and E is a separator for this graph. If you remove those, graph breaks into 2 pieces, which means I have to choose either left or right. If I go left, there's no way for me to get to right because there are no edges that cut across. I have to go through those middle guys, which means I'd have to revisit something, then that's not allowed.
Okay, it's kind of like a critical point.
Sort of, yeah, but it's called a separator set, okay? So a separator set is something where I have a left and a right piece, and there's no way for me to go from left to right or right to left, okay?
Yeah.
So if I can find these separators, this is actually useful because what's the implication of having a separator? We just said something. We said that if your path starts with those guys, A, B, C, E, I'm never going to finish it. Why even bother, right? Does it say something even more? What about A, B, C? Do you think with A, B, C can be finished?
No. because then you have to go to E.
Same reason, right? Exactly. Yeah. So you're stuck with going to E, and the same thing happens. So even you can figure this out even earlier.
Oh, so you cannot traverse the separator for...
Well, that one will only come by looking at the specific graph. It's not exactly what you're thinking. In some cases, you have to go through the whole separator in order to make sure that problem occurs. Here, the reason that occurred was because at C, you didn't have a choice. You had to go to E.
Okay.
If you had more choices, then it wouldn't quite happen.
In this case, you could avoid that, go A to F.
Right. That's right. So you have to take a different path, but can I use this somehow? How do I use this fact? That's the question. And it turns out that it's possible to figure out some rules. In this case, I will never do A, B, and C in that order. It doesn't matter at what point. It doesn't have to be immediately after. It could be A, after that if I go to B, and much later if I go to C, I'm in trouble. Because at that point, I've separated the graph, and I can't go from left to right unless I've finished everything. And so I could then generate tours that never go A before C before B. They never go A before B before C. Okay. Now these are of course much harder to code up and figure out. First of all, you have to figure this out. Then you have to somehow put it into the code. So they're a little more challenging, but in large graphs, they're actually worth some trouble. So this is what people do when they have to work with very large graphs.
That computation of like finding these nodes.
Separators?
Yeah.
Uh-huh.
That'll be less than n factorial?
Yeah.
So it's
Oh,
worth it?
yeah. Yeah.
Is it worth it?
Yeah. Much better.
How
Much.
many-
In fact, they can be done in polynomial time.
Um,
So we'll get to that at some point because that can be done using network flow.
oh.
Okay. So, for instance, what happens is that if let's go back to that. Yeah, that's a good question. So if I did, let's say I do network flow where A is my, so you guys are familiar with network flow, the problem itself?
There's like a start and a sink.
You have a source and a sink, and you have to get some fluid going from source to sink. And all the edges have capacities and all this other stuff. We don't need the details at this point. The point is that in order to get stuff from here to here, I may have to cross a separator. And the network flow approach is so well done, is so nicely formulated, that in the process of doing the network flow, you will figure out separators. And every separator is somehow useful for you. So even if you find some key separators and code it in, then it becomes valuable. So the way this could be done in reality, if you have some very, very large graphs, is do some network flow, do a few network flows. Each time find the smallest separator or find some separators. And each of these separators, you put them into a list, and then figure out whether those vertices ever get visited before you're completing. Because if you do, you're done. You're not going to waste any more time. Does that make sense?
Yeah.
So we're not going to do that, but it's just for you to understand. So it turns out if I even have one simple idea where I always, since A is the start point, it doesn't matter. If instead of going from A to B to C, I do C before B, if I just have this one little constraint, look at how much smaller the tree is, how much smaller the exhaustive search is. That's the key. Okay, so a little more work can save a heck of a lot of searching. So you have to compare this with this. Okay, and I can even add a few more things and make it smaller, but just one separator is saving us a lot of search. So in real life, when you have thousands, millions of nodes, you could save a lot of time. And so the more effort you put in pruning your search, the better, the faster it'll be. Again, it's not guaranteed. And in the worst case, you might still get n minus 1 factorial. But in real life, you never get complete graphs. And so these pruning procedures are useful in practice. So American Airlines, AT&T, whatever, all these guys who work with humongous networks, they're all going to implement these fancy things in order to do, I mean, and often they do have to do TSP problems.
If we wanted to do a road trip across the country, we just
Yeah, there you go. You got your job cut out for the next summer then. Yeah. So that's what I have for permutations and exhaustive search. Now let's try some simple variants. Somebody asked this question earlier, what if I want to generate permutations of strings? Or what if I want permutations of a bunch of numbers or something else? Right? How do I handle this? Any thoughts on this? Let's say, or let's take a simple example. Let's say I have an array, and these are all numbers. Let's say your ID numbers. Let's say one of you is 49, let's say the other is 34, 69, and 72. And I want to do permutations of these numbers. Is it simple?
yeah,
What do I do?
you have a hash table, and then the keys are true values.
I don't need a hash table, I just need an indirect address, essentially, right? Because I have indexes, 1, 2, 3, 4. I generate the indexes,
And you fill in the-
permutations of the indexes, and then I just do an indirect address of the value.
You only care about the indexes, exactly.
Correct. So I only generate the index permutations, and then when just before I print out, I change my right permutation to do this stuff.
Cool. Oh,
So I only have to change the right permutation. The code never changes.
We had a question like that, right? The ant traveling across the keyboard, where you have
Yeah,
to
that
print
one.
every.
Yeah,
I tried solving that.
that's exactly what this was, the permutations.
Permutation.
Now remember,
Yeah, okay.
I did it after the contest. Yeah, it was.
Oh, why didn't we know this before? Yeah, we didn't know till like we could brute force it.
Okay, here's your Saturday competition, mock competition problem,
Okay, cool.
right? So if it's strings, same thing, right? Easy. Then there are issues with repetitions. So, so you can make the problem more complex. So what if you're dealing with strings and there are multiple copies of the same letter? Tricky. Because you want to make sure that every permutation is unique. You can't go around doing what we did there, because two of those might end up with the same thing.
So now you're saying, oh, sorry, go ahead now. You
Go
first. I just wanted to make sure like I understand it. Like
Yeah.
you're one.
So let's say that this is also 34.
Okay, yeah. So your 1, 2, 3, 4 might be the same as your 2.
1, 3, 2, 4, and 1, 2, 3, 4 are the same.
Yeah,
So you
okay.
can't print them as separate permutations because they're not.
And it might link to the same. Okay.
So,
Yeah.
just worrying about correctness, but before we print it out, we can.
We could do that, sure. Before we print it out, we could have a hash table, blah, blah, blah. So that can be done. Can we do something smarter?
Hash and salt.
So you guys have to get your head out of hashes because that's good for for implementations, they do work fast. So I mean, I don't mean to shut that off completely, but that shouldn't be your first go-to.
Can we, okay, so, for example, the 2 and the 3, right?
Yeah.
Wait, can we just assume that 1 and 2 is 34, and then 3 is 49? Just
Sure.
for example.
Yeah. Okay.
So, okay, yeah, for those 2 right there that you have,
Yeah.
The top ones, you have 1, 2, 3, 4, then 2,
Yeah.
3, 4.
Yeah.
It would be the same thing, because 1 and 2 is 34.
Right.
Can you use check if, for example, 2 is going to point to 34,
Yeah.
and you check if that number, 34, has been in that position before? Like
But
if
that
it's
that would
40
require, that would need a hash table, right? Then you would end up with a similar solution. Can you somehow cut that off? Because there could be a lot of repetitions. This is going to make your life real hell. Well, the hash table idea makes life simpler. So that could work. But it's not, in the field of algorithms, it's not really a theoretical solution, it's a practical solution. Yeah? So, there are things that one could do. Again, I'm also thinking off the cuff here. Yeah.
Okay, this might be stupid, but let's say we take that second 34
Yeah.
and we change it to another number, not in our array.
Okay.
And when we print it, when we see that other number, we change it back to 34. No, it could lead to the same thing. Never mind.
But it'll still lead to
Yeah,
the same
yeah,
thing, yeah.
right.
Doesn't help you. So you just have to be alerted the first time this 34 shows up. And then make sure that any permutations of the other guys don't get printed, right? Yeah, maybe hash table is the only way.
So maybe have something, but maybe we make an actual graph, and then 34 should never be pointing to another 34 because of the same value, and then we can do
That's not
recursive
good enough.
backtracking.
That's not good enough. It's not a question of just next to each other. If, for instance, 1, 2, 4, 3 is the same as 1, 4, 3, 2. So they don't have to be next to each other. It's much worse than just being next to each other.
Wait, but wouldn't we go with that idea? But before printing it,
Yeah.
run through the graph and see that sequence is already in the graph.
So, so if you want to do it the old-fashioned way, it turns out that you should tackle all the 34s together. Place them. So when you do 34s, make sure that you're not permuting them, that you're placing them in distinct positions, that at least one of them moves to a different location. And you can only do that if you handle all the 34s together. So what you have to do is to take your original array, find all the repetitions, put them together, okay, and place them all.
Okay, so
When you deal with one of them, deal with all of them.
They could appear multiple times, they just
Yeah. Yeah.
So could you could have like a table where it counts how many times they appear, and if it's,
Yeah. So initially, you take your array, and well, since the order doesn't matter, let's say we sort them. So we would have all the first set of values together, then the second set of values, then the third set of values. So these are all, let's say, repeats. Right? This is what you'll start with. And then what I'm saying is you need to place these guys together, right? So in fact, when you place this, let's say these are all ones. Let's say these are all twos. Let's say this is what we have. So when I place, how does this go? Yeah, so this is where, yeah, so here's one possible solution. Again, I'm thinking off the cuff here, so I haven't really thought about this. When you place the ones, do combinations instead of permutations. So of the positions that are left unfilled, generate all possible combinations of those, and that's where the ones will go. So if there are n possible values, then n choose, there are 5 of these. I'm going to do n choose 5. I'm going to place them there. Right? And then for each of those positions, I'm going to take n minus 5. That's those positions they've been taken care of, and there are 4 of these. So I'm generating combinations of 5. I'm picking 5 locations out of the n that are available to me. Then I'm taking combinations of 4 of the n minus 5 that are remaining to me. Then here I have n minus, 9, and I'm picking 2 of these remaining. Then I have n minus 11, and of these I'm picking 3, and then of the rest I'm only going to take 1. So this is just 1. So if I did it this way, then it would sort of work out. And we know that this guy it works with index, not with the content. And so therefore, it would first start here, then it'll place this guy, then it'll place this guy, then it'll place this guy, and then it'll place this guy. The moment it has placed the last one, you have to make sure that, what do you have to make sure? So this for loop, instead of indexes, it's going to be with the groups of indexes. That's the difference. And within here, you're going to generate combinations instead of positions. I don't know if that makes sense to you. So let me draw another picture. This is the array I want to generate permutations of, right? I have n positions here. As I said, in order to place the ones, I'm going to, thank you. In order to place the ones, I'm going to pick all possible combinations of 5 out of these n. So let's say this is one combination, right? So those are all just going to be ones. Then once I place those, for each of these combinations, I'm going to go and pick the next next guys, and I'm going to pick all possible combinations of this. And that might be over here, here, and here.
How do you know it doesn't land in the same?
Because they're going to be non-zero. Remember the way the
Oh, yes. Okay.
right? So we didn't write the code for combinations. I could show you that next time. Prepare for it and show you. And so then you're just left with generating combinations from these. That would be my approach, but I'll check on this and see if there are better ways to do it. Okay? But you can see I can make the problem as hard as I want. It's progressively can be made harder. Any questions? I'm going to stop here at this point unless you have questions. So there were some nice problems here. Some were easy. This one is, of course, really trivial. This is just printing out the permutations, print all permutations. Then here was, yeah, this one looked interesting, I think. Let me see. Yeah, so it says, let's say I'm given a permutation. Why don't you read this? How much time do I have? Let's say I have a permutation. It says that for every value, I have a range within which it's the smallest, right? That's what it seems to say. So if I pick 4, of course 4 is smaller than 9, but it's not smaller than 2, and it's smaller than all these. So within this range, 4 is the smallest. So Li for 4 is this, Ri is this. If I pick 3, it's smallest over here, and so this is the range for it, right? So for each number, for each location, there is a range within which it's the smallest. Did I get that right?
We included 2?
Oh, yeah, no, we shouldn't. Sorry. Yeah. So now it's turning it around and saying, if I gave you this Li and Ri for each I, right? Yeah, given the integers for each I, you want to know how many permutations satisfy this. Essentially, it's very much related to this other question, because if 4 is the smallest here, the other guys can be permuted whatever you want, and it's going to still give you the same answer, right? So 9, 6, 5, 8 can be permuted around, and you'll still get the same Li and Ri for 4. But over here, you're given the Li and Ri for everyone, is it? Wow, okay.
Wait, is there an example problem?
I didn't see one. Oh, there is. Okay. Yeah, let's do that. So n is equal to 3, and I have 1, 1, 3. What? No. Sorry. This must be Li's and this must be Ri, is it? First line is n, second line is all the Li's, the third line is all the Ri's. Okay, good. So I have 1, 1, 3. So it's 1 and 1, which means there's only one place for 1, it seems. So 1 is at the beginning. And then I have 1 to 3. Within 1 to 3, it's 2. So is Li included or not included? Maybe Li is not included. Oh, Li is included. Okay. So I should be including 2.
And 1 for that case as well?
Yeah. Yeah, it seems like it. Yeah. And for 4, I should be including 2. So the first one is, of course, 1. 2 can be no, actually, the first one is not 1. In fact, the first one is a 3, isn't it? Because that's the one. Well, I'm confused with the Li and Ri. Let me see. Li is let's do this next time. Yeah?
Okay,
This
okay.
looks harder. This looks harder than I thought.
Yeah.
But it looks interesting. And the idea is to generate fewer permutations, permutations with constraints and restrictions. And
Do you
so
only have to do the permutations within that range, and then everything else we don't have to really worry about? Or am I reading it wrong?
not sure. So not sure. We want permutations that satisfy those constraints, right? That, for instance, that first guy, right? The first guy, 1 and 1. If Li is 1 and Ri is 1, it means that it's the smallest only in that region. So that must be 3. It must be the smallest guy. But then why are they not including the next one? So I'm a little, their notation is a little messy, so unclear. So first one is probably 3. Then the 1, 2, I think can be in either position. Yeah. So it seems to me that 3, 1, 2 is the only possible answer. Is it? Ah. I think you can also have 2 and 3.
Oh, that's why the outputs too?
Yeah. Because if I give you 3, 1, 2, it's only 1 to 1 here, 1 to 3 here, and 3 to 3 here. It seems. And same is true here. So you're not including the smaller one. So somehow their notation is not right. I have to check that again. So both of these give you the same ranges, LIRI. What is it going to be here? So easiest thing is to find the largest range, 1 through 5. That must be where your 1 is. So 1 is at the start. So 1 is at the start, and then of the remaining, 2 must have the largest range. So that's 2 to 5. That's where the 2 is, I think. So we have a 2 here. And then the 3 can be either here or here. Yeah, and if you put 3 here, then the 4, 5 order is fixed because 4 has to come first and then the 5. If you put 3, if you put 4 here, then again the order is fixed. And if you put 5 here, again the order is fixed. I think these are your 3 possible answers. I don't think anything else is possible. Yeah?
Because a 2, 2 would be any other number.
Right.
It's not including 1 or 2. Okay,
That's
so
right.
you see it.
Yeah. So it's a nice inverse problem. We can think about this. Okay? All right, guys.